For thermochemistry chapter, first we want to look at the definition for energy. Energy is defined as capacity to do work or ability to do work, and work is known as the force acting over a distance. The different type of energy, we have kinetic energy, which is energy in motion. So anything that is moving has kinetic energy, or energy that is being transferred, because thermal energy is a kind of kinetic energy. Then we have potential energy. For potential energy, energy is stored in an object or energy associated with the composition and the position of an object. So if we have an object that is at the higher elevation compared to the ground, that object has potential energy. If you let it go, it will fall. And as it falls, the potential energy is going to change to kinetic energy. So if you have something moving, an object is moving, it contains kinetic energy. The law for conservation of the energy states that energy cannot be created or destroyed, and it can be transferred between the objects. It can change from one type to another type. It can go from one form to another form as well. So heat, light, sound, these are all different types of energy that they can go from one to the other types. We have some other forms of energy: electrical energy, heat energy, and then we have the light, nuclear energy, chemical energy, different types of energy, just to know the different type. Units for the energy, they can be in joules, and 1 joule is basically 1 kilogram. 1 kilogram times meter square second square. So it's the definition for the joules. How much is 1 joule? Basically the amount of the energy that is needed to move 1 kilogram mass at the speed of 1 meter per second. So that would be the energy that is 1 joule equivalent to 1 joule. So other units for the energy could be calorie. So we have joules, the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. That's in 1 second. So that's the amount of the energy. And then calorie is the amount of energy needed to increase the temperature of 1 gram of water by 1 degree Celsius. Calorie, if you notice that calorie is a lowercase c. If you have a capital C for calories, that equals actually kilocalorie, and that's what is used for the food calorie and kilocalorie. So instead of saying kilocal, they just use capital C, and that means is kilocalorie, which is like a 1,000 calorie. The units, to convert between the units, you can go from calorie to joules. 1 calorie is 4.18 joules, and 1 kilocalorie is 1,000 calorie, and 1 kilowatt hour, that's another unit for the energy, that equals 3.6 times 10 to 6 joules. That is a large amount of heat. That's you can see in some problems. So these are some examples just to make sense out of just to be able to make sense out of these numbers. Joules, it's like the amount of the energy that it can raise the temperature of 1 gram of water by 1 degree Celsius, that you would spend 4.18 joules, or you would spend 1 calorie, or you would spend 0.001 kilocalorie. It's the amount of energy required to light a 100-watt bulb, light bulb for 1 hour. That would be 3.6 times 10 to 5 joules, and that would be 8.6 times 10 to 4 calorie, or 86 kilocalorie, or 0.1 kilowatt hour. So just to make sure that you get the sense of how much heat is needed for different process. When you're dealing with the energy, you have to make sure that you specify your area of the study. So you're talking about, let's say, if you're talking about the system versus like surrounding, the system is defined as material being studied for the energy change within. So if you are studying the change in energy inside this area, or the material that is in this content, you would talk about system. Anything outside of that is going to be surrounding. So when the energy is given from the system to the surrounding, the energy is for the system is going to go lower, and the energy of the surrounding, it would increase. So energy, if it's given off by the system, the internal energy for the system would be lowered, and then the surrounding basically gain energy. Internal energy is the total amount of energy, and that includes the kinetic and the potential energy of a system. So change in internal energy of a system only depends on the amount of the energy in the system at the beginning and at the end. So how much energy was system had, total kinetic and potential, at the beginning, and at the end, what is the total amount of energy. And the difference between the two is changing the amount of energy. So a state function is a mathematical function. This result only depends on the initial and final condition. So change in energy or change in internal energy is also is a state function. That means that energy, the change in energy, it does not depend on the route. It just says how much energy was the system had at the beginning and how much energy the system has at the end. So if the energy, internal energy goes up, that means energy has been absorbed by the system. If the internal energy goes down, that means energy has been released from the system to the environment. So when the system releases energy, the sign that is used is a negative. System can do work and lose energy, or system can release energy, or system can release heat. In either case, the sign would be negative. That means system is losing energy and the internal energy would be lowered at the end. When the energy is gained, it can be gained by the system. It can be like the system gains energy from work, or system gains heat. Heat is applied to the system. Then the energy is being increased, internal energy is being increased, and the sign for that change in energy is going to be positive. So energy is always exchanged between the system and the surrounding. It can be done, that can be done via heat or work. The amount of the energy, how can be calculated? The amount of the energy, Q is the symbol used for the energy. It depends on change in temperature, and it also depends on the heat capacity. So if the heat capacity, it's going to be then the amount of energy needed to increase temperature, let's say by 1 degree Celsius. So when you say heat capacity joules per degree Celsius, that means the number of joules or the amount of energy needed to increase the temperature by 1 degree Celsius. So if you have the heat capacity for any system, if the temperature increases by 1, then the Q is going to be equal to heat capacity. If the temperature is increased by 10, then the amount of the heat needed to increase the temperature by 10 is the heat capacity times 10. And then you can also calculate this different amount using different quantity for the temperature and the heat capacity. When you talk about specific heat capacity, it has a different definition. Specific heat capacity is the amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. So is the joule per gram per degree Celsius. In that case, the unit or the formula for Q is going to be different. Now you have to talk about the mass because that's the gram, and then times specific heat times changing temperature. So the amount of the heat is going to be calculated based on the mass, based on specific heat, and based on changing temperature. So we have that new formula. So C times change in temperature or heat capacity is used when we are not dealing with the mass and specific heat separately. But when we are dealing with a specific heat, then you have to include the mass. Because if you have a heat capacity, is the heat capacity for the whole system, change in temperature by degrees Celsius. Molar heat capacity, it would be the amount of the heat that is going to increase the temperature of 1 mole of a substance by 1 degree Celsius. So a specific heat is for 1 gram by 1 degree Celsius. Molar heat capacity is going to be the amount of the heat needed to increase the temperature of 1 mole of substance by 1 degree Celsius. So when the information is given for a problem, you have to pay attention to, is it giving heat capacity? Is it giving specific heat capacity? Is it giving molar heat capacity? What information is given before you start using the value or the formula for calculating Q or the amount of the heat. But if Q is calculated, is based on mass, change in temperature times specific heat. If you have Q, you can actually divide by molar mass or find it based on number of mole, and you can convert that heat to the molar heat capacity. Or a specific heat times molar mass, that gives you molar heat capacity. You can calculate the quantity of the heat absorbed or released using specific heat, mass, and change in temperature. So because the heat, if you just talk about the heat capacity, because it's proportional to its mass, the higher the mass, the higher the heat capacity is going to be. But it's easier to separate the two and use the mass times specific heat capacity, which is expressed based on a gram. Okay. It's per gram per degree Celsius. This is let's say if it's a joule, it's going to be per gram per degree Celsius. That would be unit for a specific heat. Okay. How much heat is absorbed by a copper penny with mass of 3.1 gram, whose temperature rises from -8 to 37 degree. So if you have the formula for Q equals mass times change in temperature times a specific heat. So see what information we have here. We have the mass 3.1. So we can say 3.1 gram. Change in temperature is the final temperature minus initial temperature. So 37 minus -8, that gives you the change in temperature, which is equal to 45 degree. The unit, if it's Kelvin or if it's degree Celsius, it doesn't matter because you're looking for the difference. So in this case, you have 3.1 gram times 45 degrees Celsius times a specific heat for copper. So what is the specific heat for copper? You must have that value. If you have that value as the 0.385, so it would be 0.385, and we have the unit for that, joule per gram degree Celsius. Okay. Joule per gram degree Celsius. Then we can cancel the units. Gram would be canceled with this gram, degree Celsius would be canceled with degree Celsius, and the number that you find here is going to be expressed in joules. So we have 53.7 joules. That's the amount of the heat needed to increase the temperature of this copper penny from -8 degree to 37 degree Celsius. And from now on, anytime you want to calculate the amount of the heat for being absorbed or being released, you can go with the using mass change in temperature and specific heat capacity. So heat can be absorbed or released by the system. If the heat is absorbed, then the internal energy would go up for the system. The sign is going to be positive. If the energy is released to environment, the sign is going to be negative for that system. Okay. We have now a different problem, like a bomb calorimeter, when basically is a insulated equipment. If the energy is released inside this calorimeter, that energy is going to be spent to show the change in temperature. So the temperature is going to go up. The higher the temperature goes up, more energy has been released. So in order to calculate or to do calculation of how much heat has been released, so in this case, you have the mass, 1.1 gram of sugar is burned in bomb calorimeter. The temperature rises from 24 to 28. And if the heat capacity, this is the heat capacity is given for the calorimeter. The heat capacity, meaning the amount of the energy needed to increase the temperature by 1 degree Celsius. So if it's changed by 10 degrees, it would be 10 times this value. If it's changed by 15 degrees, so you have to multiply by the change in temperature. So in this case, remember, if the heat capacity is given, there is no mass involved. You don't have to use the mass. The heat capacity for the calorimeter is given times the change in temperature. So if we have the heat capacity already, and you find the heat for this, you find the heat for reaction, then when you find the value for the heat, and you divide that by the molar mass, you would find the amount of the heat being released per mole. Okay, so you find the you are going to find the Q. To find the Q, we need, as I said, we need the heat capacity, and we need change in temperature. Change in temperature is the final minus initial. So we have the change in temperature is going to be 28.33 minus 24.92. The solution is also shown here. I just want to show you the steps. The value for C of calorimeter is given to us, so it's a 4.9. So this two value, if you want to find the delta E, or the Q value, the amount of the heat first, let's find the Q, which is C of the calorimeter times the change in temperature. So when you find this value, then on the next step, because it's asking for the molar, okay, is asking for 1 mole. So when you find this value, this is for the given gram, for that grams. But we want to find out how much is going to be per mole. Basically is asking to find the value for delta E. This is per mole. For delta E, we need to find the Q for this reaction, which we are going to find from this equation. We have the value 4.9 times delta T, which is the difference between the two numbers. And then we are going to find the mole. So to find the mole is going to be mass over molar mass. So you have the delta E equals Q of the reaction, whatever you find, and then this is going to be 1.01 divided by molar mass for this compound, which is 342.3. And whatever the number is going to be calculated as the delta E, or the amount of the heat released per mole of that sugar. Okay, so we will find the value for Q. We will find the number of moles, and we divide the Q by the number of moles in order to find the delta E, or the amount of the heat per mole. Enthalpy of a system is the sum of the internal energy of a system. And the enthalpy, or change in enthalpy, it's basically the amount of the heat for the reaction. So delta H for a reaction is same thing as the heat of a reaction at constant pressure. So basically, if the pressure is constant, so enthalpy, if it's energy plus the work, or the pressure times the volume, at constant pressure, if the pressure stays constant, enthalpy is only related to the energy, And change in enthalpy, or the change delta H for the reaction, the delta sign is for change of the reaction, is the change in the energy caused by the reaction at a constant pressure. If the delta in and delta H, as it says here, they are similar unless the reaction involves with a large, change in number of moles of gas. That means there would be a huge change in pressure, and that is going to make the contribution to the delta H value. For a reaction that is exothermic, the sign for delta H is going to be negative. That's for exothermic reaction. That means internal energy is going to go up. That means product is going to have more energy than the reactant. I take it back. The energy, when it's negative exothermic reaction, energy is being released. So when the energy is released, that means that the reactants, they have higher energy compared to the product. So if this is the energy line, you have the product, you have your reactants. The difference in this amount of energy is the delta H that is going to be released to environment. So internal energy actually is going to go down. The product have less energy than the reactant. The difference in energy is going to be released. This is for exothermic reaction. For endothermic reaction, if it's an endothermic reaction, it's the opposite. We have the reactants, they have lower energy. Products, they have higher energy, and this is the transition state. So products, they have higher energy. This amount of energy needs to be provided to the reactant to change the product, because product need this amount of energy. They have more energy than the reactant. So we have endothermic type reaction. So the sign for delta H is going to be positive. That means energy has been gained by the reactant in order to change the product. For exothermic reaction, delta H is negative. That means energy has been released. For the endothermic reaction or exothermic reaction, there are bonds that are broken. Bonds are in a chemical reaction. Bonds are broken, bonds are formed. When bond is broken, energy is consumed. When bonds are formed, the new bonds that are formed, the energy is being released. Now, if more energy is released than the amount of energy that is being consumed, overall energy is going to be released. If more energy is being consumed than what is being released, then more energy is being consumed, and that is endothermic type reaction. So for a change in enthalpy of the reaction, or delta H of the reaction, for a chemical reaction, when delta H is negative, that means this is the exothermic type reaction. And this is for the reaction based on the balanced equation. So what does it mean? It means that if 1 mole of C3H8 or 1 mole of propane is combusted or goes through combustion reaction, reacts with 5 moles of oxygen, is going to release this amount of kilojoule of a heat, 2044 kilojoules of the heat. The number of moles of oxygen that is needed in this reaction is 5 mole. So if 1 mole of propane, 5 moles of oxygen is combined, this amount of the heat is going to be released. How do we know it's going to be released? Because the sign for delta H is negative, and that means exothermic type reaction. Now, how much heat is evolved or released in a complete combustion of 13.2 kilogram of that? So in order to do that, we know that for every mole, it's 2044 kilojoules heat being released. So if we know how many mole is this, so for 1 mole, minus 2044. For 2 moles is going to be 2 times minus 2044 heat being released. For 10 mole is going to be 10 times this number. And for this number of moles, whatever we have here, number of moles, is going to be number of moles times this delta H value. So in order to find how much heat is going to be released for 13.2 kilogram, first we want to find out how many mole is going to be. In order to calculate the number of moles, you need the molar mass for propane. Molar mass for propane is calculated based on 3 carbon, 3 times 12, plus 8 times 1, and that is a 36 plus 8 is going to be 44 gram per mole. So we have 44 gram per mole, that's where it's coming from. And then we want to know how many grams we have. So since we have kilogram, first we convert to gram. So you convert the kilogram to gram, then you divide by 44 to get the number of moles. So if you have the number of moles times the delta H, that gives you the total amount of heat being released if 13.2 kilogram of the propane is being consumed. To measure the delta H or the energy change in the chemical reaction, you can use a calorimeter, and then delta H for the reaction, or delta H of the reaction, is like per mole. So you find the Q, just like before, you find the Q of the reaction, which is the mass times change in temperature times the specific heat. Or if you have the heat capacity, then it's going to be Q of the reaction is going to be the heat capacity of the calorimeter times in change in temperature. So either you have both mass and the specific heat, or you have the heat capacity and the change in temperature in order to find the Q for the reaction. When you have Q for reaction, in order to find the delta H for the reaction, you would say Q for reaction divide by number of moles. So that gives you the Q for reaction. So this is for 13.2, the sign is negative. So let's look at the next step. What is the delta H per mole of magnesium for this reaction? So we want to find the delta H per mole of magnesium. First of all, you need to find the Q value. The Q in this case, we have to look for if the mass is given, and then change in temperature is given, if a specific heat is given, or a specific heat needs to be provided to you. Then you can find the value for Q. When you find the value for Q, then you are going to divide that Q by moles. So for delta H, first you want to find the Q of the reaction, and then you divide that by mole of Mg. To find the mole of Mg, is mass of Mg, capital Mg, mass for Mg, which is given as the value you have here, 0.158 grams, divide by molar mass of Mg. The molar mass for Mg is 24. So that's a gram per mole. So from that, you find the moles of Mg. So we need the moles of Mg and we need the Q for the reaction. Q for the reaction, if a specific heat is given, mass is given, change in temperature is given, you just use the reaction. Mass, specific heat, and change in temperature. The specific heat, because the temperature of the water is changing, the amount of the water is given 100 milliliter, 100 milliliter, 100 milliliter of water. 1 milliliter equals 1 gram of H2O. 1 milliliter H2O equals 1 gram of H2O, because density for water is given as 1 gram per milliliter, or density for solution is 1 gram per milliliter. That means 1 milliliter equals 1 gram. So if you have 100 milliliter, that would equal to 100 grams. So we have 100 gram of the sample. The specific heat is assumed to be 1 calorie, or 4.8 joules. So we have the specific heat as 4.18 joules per gram per degree Celsius. Delta T is the final minus initial. So we have the 32.8 minus 25.6. That gives you the value for delta T. So if we have these three values, we can calculate the Q. So if we have the Q of the reaction, we can calculate delta H. Delta H is Q of the reaction divided by mole of the magnesium. And if we have the Q of the reaction calculated already, divide by the mole of the magnesium, you get the delta H for per mole of magnesium. So just keep this in mind. Delta H is related to the Q of the reaction, and then you have to apply the number of moles. Delta H is Q for the reaction divided by mole of the substance. Delta H for a reaction, if it's given, is a reaction specific. So delta H for this balanced equation is minus 293.5 kilojoule. Now, if you double this reaction, you multiply the whole reaction by 2, you are going to multiply the delta H also is going to be 2 times 2, okay? So you are going to multiply by 2. So if you divide, the divided is going to be divide by 2, you would divide the delta H value by 2. If you reverse a reaction, when you reverse a chemical equation, the sign for the delta H is going to be reversed. So a CO2 generates carbon plus O2. This is a reverse reaction. The sign is going to be also reversed. Based on the Hess's law, if the reaction can be expressed as a series of steps, then the delta H for the overall reaction is sum of the delta H for the multiple steps. So if delta H3 equals delta H1 plus delta H2, then you can basically add the delta H1 and delta H2 to get the numerical value of it, to get the value for delta H3. Means that you have one exothermic reaction, one endothermic reaction. The overall amount of energy can be calculated by adding these two, delta H1 and delta H2. Is known as the Hess's law for the change in enthalpy, or delta H for a stepwise process is the sum of enthalpy changes of all the steps. This is the Hess's law, and you are going to use facts that if you reverse the reaction, the sign for delta H is going to be reversed. If you double a reaction, delta H would be doubled. If you divide a reaction by half, the delta H value would be also divided by 2. So we have to pay attention to these 3 reactions. How can you rearrange these reactions in order to come up with the overall reactions that we have here for the delta H, 3NO2 and H2O? It yields 2HNO3 plus NO. We want to find the delta H for this. Well, we don't have the delta H for the reaction, but we have delta H for these separate steps. Now, I want the NO2 to be on the reactant side. So I'm going to look at this first reaction and say, okay, NO2 is on the product side. How can I bring the NO2 to the reactant side? I have to reverse the reaction. So I have to reverse this reaction. In order to reverse it, I have to say 2NO2 yields 2NO plus O2. If I reverse that, the delta H value is going to be also reversed and it's going to be plus 173. Now, we have also H2O on the reactant side. So if I look at these 3 reactions, H2O here is on the reactant side. So I'm going to have to keep this as the H2O on the reactant side. So I'm going to keep that. But I only have one H2O, okay? If I have only one H2O, how I'm going to change that to one H2O? I have to divide this whole thing by 1/2, okay? Divide by 2. If I divide all all of the coefficients is going to be divided by 2, and this value for delta H needs to be also divided by 2. Then N2 is going to be canceled. So N2, in order to cancel the N2, I have to reverse this reaction. So this reaction is going to be reversed. If it's reversed, it's going to be 2NO yields N2 plus O2. And the delta H for this one is going to be minus 181 kilojoules. So let's see what else we need to do. This reaction, I have 3NO2. Okay, I have 3NO2, and I need 3NO2 here, but I have only 2NO2. So I have to multiply this whole thing by 1.5 because I have to have that 3NO2. And if I multiply that by 1.5, delta H is going to be also multiplied by 1.5. So it is reversed and is going to be multiplied by 1.5. And each time you're going to have to write these steps like separately. So if I'm going to multiply, so my first reaction is going to change now this way. It's 2 times 1.5 is going to be 3NO2 yields 2 times 1.5 is going to be 2 times 1.5 or 3NO plus 1.5 O2. And then delta H is going to be plus 173 times 1.5. That's first reaction. Second reaction, we said we are going to divide everything by 2. So second reaction now is going to change to N2 yields, N2 plus 2.5 O2 dividing by 2. I'm dividing by 2 plus H2O. it yields 2HNO3, and then the delta H2 is going to be 2 is going to be 255 divided by 2. What happens to reaction 3? What did we do for reaction 3? Reaction 3, the third reaction, is going to be times 2, because was it times 2 or reverse? It's going to be just reverse. Just reverse. So it's going to be 2NO yields N2 plus O2. And delta H3 is minus 181 kilojoule. Okay, let's add all the first, second, and third reaction together. If you add the first, second, and third one together, basically what we are doing, we are drawing a arrow, and anything on the left side of the arrow would go to the reactant. Anything on the left side of this red mark now is going to go on the reactant side. And then anything to the right side would go on the product. Like term is going to be canceled from both sides. Before you add, you can try to cancel the like term from opposite side. So N2 from second reaction on the reactant side, N2 on the product side is on the product side, and from reaction 3, those two can be canceled. O2, final reaction doesn't have any O2. We have 2.5 O2 here on the reactant side, and then this is on the product side. 1.5 of it is going to be canceled with 1.5 of this. 1 is left, and this 1 is going to be canceled with this 1, because this is on the is also on the product side. 1.5 O2 and 1 O2 is 2.5 O2, and then that would cancel with the 2.5 O2 on the reactant side from reaction 2. So we canceled the O2 as well. The NO, we don't have the NO on the product on the final reaction anyway, so we try to cancel it. We have 2NO on the product side of reaction 1, and then 2NO from reaction 3. We can cancel it all. Now we're trying to add these 3 reactions together. Anything that is not canceled, it will go as the final reaction. What is not canceled, I'm going to circle with the purple color because I don't have room to write it down. It's going to be 3NO2 on the reactant side plus O2 on the reactant side. Nothing is left from reaction 3. And then on the product side, we have 2HNO3 plus plus 1NO. So if we have here the 3NO, sorry, we have the 3NO, and if we have 2NO, 3 would be canceled with 2 of this would be canceled with 2, and 1 is left. So it's going to be 1NO that is going to be on the product side. So that basically gives this reaction what we had to come up with. It does take some practice to try to figure out, but your starting point would be to look at the final reaction that you want to come up with, and then decide to change these reactions. Since NO2 it's on, I'm just repeating, NO2 is on the reactant side, we know that we have to reverse this reaction. We have to reverse the first reaction. We have 3NO2, and on the reaction we have 2. That's how we multiply by 1.5. So first reaction needs to be reversed and multiplied by 1.5. Second reaction only needs to be divided by 2. Third reaction needs to be reversed. How do we know the third reaction needs to be reversed? Because NO was on the reactant side, so we have to be able to cancel with this NO on the product side, and then we want to be able to cancel the NO from the first reaction. So this part has to come to the reactant side. So we should be able to cancel it, and we have to be able to cancel the O2 as well. Then when we add all these 3 revised reactions, anything happens to the reaction, same thing will happen to the delta H value. So reverse reaction together, we come up with the final reaction. You do the same, you add the same thing for the delta H values, and then you come up with the overall number here for the minus 49 kilojoule for that new reaction. This is known as the Hess's law to find the delta H. Another way to find the delta H of the reaction is use the delta H formation. What is delta H formation? Is the amount of the heat that is being released when one molecule is made from its element. So if carbon plus O2 is combined and it gives CO2, and you find the delta H for this reaction, because it's formation of CO2 from a carbon and O2, which are the elements, this delta H can be also recognized as the delta H formation for CO2, because is the formation of CO2 reaction that we are calculating, or we are finding the delta H value. Delta H formation, it can be at the standard condition. The standard condition is a 25 degree Celsius and 1 atm pressure. And if you put the standard, then you would do this like a sign of standard delta H formation of compound from its element. Delta H formation or standard delta H formation for a compound is given in tables. Those values can be available to you. Delta H formation for element, let's say if you have a sodium in solid phase, this is how it appears in nature. So that value is going to be 0. Delta H formation for Na solid equals 0. Delta H formation for O2, because that's how it appears in nature, delta H formation for this is going to be 0. Delta H formation for O2 is 0. Okay, but delta H formation for CO2 is not 0, because that's not, it appears in nature. So delta H formation, it can be used in order to find the delta H for a reaction. So delta H formation for CO is coming from graphite and is coming from O2, that is 1 mole of the CO that is forming. And if you want to have like 1 mole of the CO, the O2 needs to be divided by half. This is the only case that the coefficient can be fraction. For expressing delta H formation, the product has to be 1 mole. So if product needs to be 1 mole, then we have to use 1/2 of O2, because it's diatomic in nature. So very rare this happens, only for delta H formation. Now, if you want to calculate the delta H of a reaction, delta H of reaction would be delta H formation for all products minus delta H formation for all reaction. So this symbol is basically shows as the sum. You add delta H formation for all reactants together. You add delta H formation for all products together. and then subtract the value of the reactants from the product, and that gives the delta H of reaction. Okay, let's look at this example here. Delta H formation for CO2 is given, for C2H2 is given. These are delta H formation, and for H2O is given to us. If we have the value for delta H formation of all these three compounds, we have for C2H2, we have it for CO2, and we have for H2O. What's the value for O2? O2, because it appears in nature as a diatomic molecule, then the delta H formation for this is going to be 0. Okay. Now, if you want to find the delta H for delta H reaction, that's for this reaction, you want to add all the products and the reactants. So for the products, you have what are the products here? You have the products minus the reactant. So we want to make sure it's going to be sum n products, okay? Delta H formation of products minus sum n delta H formation of reactants. So what does it mean? What does this n value means? It means that if you have 2 moles, you have to now multiply by 2. So for the products, what do we have? We have 4 CO2 and we have 2 H2O. So we're going to add the products together, and that is 4 times value for CO2 is 393.5 plus 2 H2O, and that's, we have the 2 H2O, 2 times minus 285.8. This is the delta H formation for all the products. That's what we have. Minus, we open another bracket because we want to add them all up. Delta H for reactant, we have 2 times the 2 to 7 plus the other reactant is 0. You have to, this is like a simple math, but you have to be patient and you have to do one step at a time, and you are able, then you can actually find the delta H for this given reaction, because you are applying the number of moles is not per mole of C2H2, it's for this balanced equation. So when you're given the delta H is for reaction specific, and that is for this balanced equation. Okay, this is the value 2600 is calculated, but I showed you have to do the calculation for it. Delta H reaction 4 times this minus plus the 2 of the water minus. So here bracket is not used like in between. I prefer to use the bracket, so I know that I'm using the PEMDAS. Okay, I'm using the PEMDAS. So I do calculation for this part, I separately that part, and then I subtract. How many kilograms of octane must be combusted to supply this amount of the heat? And what do we have? Do we have the delta H of the reaction? If we don't have delta H of the reaction, first we have to find the delta of the delta H for the reaction. In order to find the delta H of reaction, we need the delta H formation for octane. This is going to be 0. We need the CO2 and we need the H2O. Then we find the delta H, find the delta H for the reaction. Delta H for this reaction, delta H of the reaction is going to be sum and product minus the reactant. So it's going to be 8 times delta H for CO2, delta H for CO2, plus 9 times delta H for H2O, minus delta H for C8H18. That's 1 times that, plus 25/2 times 0. Okay. So this is going to be 0, and then you do the calculation. This is the delta H for 1 mole. Okay, that's whatever this number is for 1 mole. 1 mole of C8H18. But if you want that much of the kilojoules, for every mole, you find it for every mole, and then you have to divide that by the energy, by the delta H value, in order to find for how many moles is going to take. So we already know the delta H values for these, and you find the value for delta H of the reaction, and then you divide the wanted energy by the delta H value. That gives you number of moles. Okay, so you can calculate delta H based on given delta H value for other reaction, basically using Hess's law. You can calculate delta H based on delta H of formation. You can calculate delta H based on one reaction, which gives you Q value, which is mass times change in temperature times specific heat. And then you divide that by number of moles. Basically, that's like delta E that equals to delta H if there is not much of gas involved, moles of gas involved. And then you have 3 separate ways to find the value for delta H. One, I'm just summarizing for you, delta H values